Welcome back, everyone, after lunch. I hope you did enjoy the lunch and had the possibility to try some wine as well. We will start with the afternoon session with UBS. We have 3 people presenting right now. The first one in the line is Mavrodiev, who works as a full-stack data scientist at UBS. He holds a PhD in complex systems from ETH Zurich. He's passionate about the complete pipeline enabling data-driven products, from data engineering to data science to model development. At UBS, he contributes to AI solutions in the domain of pricing and sales. He is the chief architect of the Algorithmic Fairness Toolkit at UBS. Next, we have Sritama Basu. She's a data scientist with more than 10 years' experience in developing machine learning solutions and applying statistical analysis for diverse domains with strong regulatory oversight. Her qualifications include full-stack data scientist, from problem formulation to data engineering, and from model optimization to communication with stakeholders. Along with both of them, we have Yuntao Li, who is also a full-stack senior data scientist at UBS. He's passionate about also building end-to-end AI and ML pipelines for delivering business value. At UBS, Yuntao mainly focuses on developing AI solutions for lending and sales. As a core developer and methodology lead of the Algorithmic Fairness Toolkit at UBS, he's passionate about infusing social responsibility into AI ML use cases. Yuntao holds a PhD in physics from Georgia Tech, USA. All 3 of them will be presenting on the topic responsible use of AI ML at UBS, incorporating algorithmic fairness in real business settings. Anyone working in AI must be familiar with the topics such as bias, fairness, and responsible AI. With several federal laws such as EU AI Act, EU Data Protection Act, and so on, it has become an absolute to bring fairness and responsibility into AI products. This talk will focus on how UBS incorporates fairness and responsibility into data and AI-driven solutions. Welcome to all of you.
Yeah, thanks a lot for the introduction, and also thanks everyone for joining us. I'm Yuntao, this is Sritama, and this is Pavlin. We're all data scientists from UBS. And it's also good to have Manuel Proizo in the audience, who originally contributed a lot to this work. So at UBS, we have been developing in the past year or so an internal solution for algorithmic fairness. Or in other words, we're trying to help ensure our AI and ML models and data are fair quantitatively. And today, we would like to share our insights and some learnings via a real business use case. And of course, hope to spark more discussions around this important topic. But first of all, why would we care about fairness in machine learning? Well, as a financial institution, reliability, transparency, and trust lie at the heart of all services provided by UBS. We have seen many cases where it's not just the additional features, added values that matter to our clients, but also the confidence, the peace of mind that they gain from us. And also, as we leverage data analytics more and more from different angles, it's crucial that these applications also share the same level of trustworthiness. And for that reason, we really need a principled way to measure and even mitigate any biases or unfairness in the data and models. And in fact, algorithmic fairness is not just a nice to have, but also soon going to be an imperative, as we have seen so many active developments in the regulation space. So we all know this instrumental European AI framework, where transparency and fairness are specifically mentioned. And other countries like US, Singapore, China are also ramping up their efforts by introducing legislations and white papers and guidelines. So I think we are really at dawn of algorithmic fairness. And there can only be more and more initiatives to standardize how these techniques should be applied. So our solution at UBS is called UBS Fair. So it's an end-to-end framework to tackle fairness or unfairness in data and models. So it started out as a very fruitful collaboration between UBS and ITSIA, so the Swiss AI Institute. We first developed a prototype for mortgage pricing by eliminating correlational effects from sensitive data attributes such as gender and age. And from there, we really see a need to understand their impact, I mean, the impact of these sensitive data attributes from a causal perspective. So we also came up with a new algorithm called fair Bayesian networks. But the most important outcome of this initiative is a Python library with the same name, UBS Fair, that enables fairness considerations throughout the whole life cycle of data science. So all the way from data pre-processing to monitoring and reporting. So more concretely, with UBS Fair, one can pre-process the data into a new representation with less bias, or one can directly build fair models by introducing fairness constraints during the training process. And more flexibly, one can even take any pre-trained model and just post-process predictions so that they become fair. And on top of that, we also provide various metrics and visualization widgets to help report and summarize the results. So with the current release, this tool can be applied to any structured data, so numerical or categorical. It can handle both regression and classification models. And implementation-wise, we have carefully chosen a set of state-of-the-art research from the literature, including various evaluation metrics and mitigation algorithms. And of course, we didn't create the tool to be just a shelfware. It has actually been applied to several internal use cases just to learn that how we can conduct fairness analysis in a real business setting. So next, Sritama will walk us through a very interesting example.
Thanks, Yintao. So with that overview, I will dive into one of the pilot use cases where we applied fairness analysis. And this is the client digital affinity model. So very simply, this is a supervised ML model which tries to predict the client's preferred channel of communication. So whether the client prefers digital modes of interaction or more in-person, face-to-face meetings. And these are the key steps that we have identified in the fairness analysis workflow based on our experience of applying fairness analysis on a few use cases. So firstly, we start with a very thorough and complete understanding of the business and operational context of the use case, and based on which we are able to identify the relevant sensitive metrics. And the sensitive metrics are the ones, the client features with respect to which we want to ensure non-discrimination or algorithmic fairness. So for this use case, we chose age, civil status, and domicile. And next, we define the subgroups for these features, because whenever we talk about fairness, it is usually in the context of a subgroup for the population. So once we have the sensitive features and the subgroups defined, we need relevant fairness metrics with which we can quantify and measure fairness or unfairness in the data and model. So here we have chosen disparate impact ratio and equalized opportunity to frequently used group fairness metrics from the literature. And with these metrics, if we identify a bias, we need a bias mitigation algorithm. In this use case, we have applied individual group debiasing. It's a post-processing algorithm, meaning it works directly with the output from the original model, which is optimized for fairness, and then it is able to apply fairness constraints and obtain fair predictions. The final step is to analyze and interpret the results and link it back to the implications for both the business and societal impact of this analysis. So we can start looking at the results. So the first sensitive feature is civil status. In this case, it was a binary variable, married versus not. So it comes from one-hot encoding, and the not married category actually contains all the different categories under civil status, except for married. And here, with these two fairness metrics, we can see, so these metrics are, with these plots, it's very intuitive to interpret whether there is a bias or not. So the ideal values for these two metrics are 1 and 0, respectively, and any deviation in either direction indicates that some bias was indeed detected. So for civil status, we observe low bias from the ground truth, which is used to train the model. But when we look at the computed metrics from the predictions of the model, we see that with both the metrics, there is a deviation from these ideal optimal values, indicating there is a bias. And we see that the performance of the model is much better in the married subpopulation compared to the non-married subpopulation, with a true positive difference of 23%. So with this obvious bias detected, we apply the individual group debiasing algorithm, and we are able to obtain fair predictions, which are quantified through this the metric in green. So these are again back to the ideal desired values for the two metrics. So in this way, we can see, using these metrics from the literature, we are able to quantify and detect bias, and with these debiasing algorithms, we are able to remove this bias and obtain fair algorithms, fair prediction from the algorithms. The next use case, the next example is the age attribute. So our goal here is to ensure non-discrimination, equal quality of client services for all age groups. And age here is a continuous variable. So how do we define subgroups here? We took the different quartiles of the distribution and used this to threshold the population into a younger than and an older than subpopulation. And this is what we see along the x-axis for the plots. So in this way, by thresholding the population with different age threshold, we are obtaining several different stratifications and are able to conduct a very thorough and robust analysis. So with these two metrics, again, disparate impact ratio and equalized opportunity, here also we observe that the bias from the data, which is used to train the model, indicates that there is higher adoption of digital channels for communication in the younger population. So this observation in the context of this use case is likely a reflection of the preference of the clients rather than a discriminative bias. And when we look at the predictions from the model and compute the metrics, we see a very obvious trend of increasing deviation in the blue crosses. I don't have a pointer, unfortunately, from the ideal values. And this increasing trend of deviation indicates that the model performance is increasingly poorer in the older parts of the population. So with this bias detected, we apply the individual group debiasing algorithm and are able to obtain the metric values, which are, again, closer to the ideal optimal values for the fairness metrics. So we observe a relative reduction, but we see that there is still some level of residual bias with these metrics. So this example shows how we can apply this sort of debiasing for a continuous attribute. The next sensitive feature was domicile. So here it was a binary attribute, urban versus non-urban. And the observations here were, again, similar to the past two use cases. The bias detected with these metrics, we were able to mitigate with the help of the individual group debiasing algorithm. So one important thing is, whenever we perform fairness analysis, we have to monitor simultaneously not only the fairness metrics, but also the performance metrics. So in this case, we have F1 score. And F1 score, it's a combination of precision and recall of the model. So the original model, which is optimized only for performance, was in fact optimized for precision. We see in the blue cross the corresponding values. So the original model had high precision, but the corresponding recall was rather low. And once we apply the fairness intervention, the fair model that we obtain improves greatly with respect to recall, but there is a small drop which is observed for precision. But the resulting F1 metric, which shows the overall performance of the model, there is an overall improvement. So these sort of trade-offs have to be simultaneously monitored for both the various performance metrics as well as the fairness metrics. So in our experience of applying this fairness analysis to a few use cases, we have collected the open questions and challenges that we have frequently encountered. And these are mostly about how we select the relevant fairness attributes, the sensitive attributes and protected groups, how we choose the metrics from the many different metrics which have been proposed in the literature, and then interpret the changes in the values of these metrics. So firstly, fairness analysis is extremely context dependent, and the contextual information needs to be taken into account to determine which are the most important sensitive features. So generally, the sensitive features are informed by anti-discriminatory laws and regulations, and then further prioritization among them can be done depending on the context of the use case, so which could potentially lead to the most vulnerable or disadvantaged subpopulations. And another aspect to always consider is the proxy variables. So these are variables which can encode information about the sensitive attributes. For example, in this use case, we had domicile, which appeared as an unusual choice. And this is informed by some of the other studies in the fairness literature, which showed that in some cases, the encodings of domicile could reveal racial or other socio-economic information about a person. Choosing fairness metrics, so this is often quite challenging, and this is because in the literature it's been shown that not all the different fairness metrics can simultaneously be optimized, and hence, depending on the use case context, one has to prioritize which are the most impactful types of errors, and based on that, choose the relevant corresponding fairness metrics. Finally, to interpret the results, so we observe that with real data, we often have a relative reduction of bias, but don't obtain a perfectly fair model. So the implications of this residual error and the risk associated with that in the context of the use case is to be addressed taking into consideration expert input, so domain knowledge and knowledge to ensure that both the model risk and performance is simultaneously addressed. So overall, with these different points, we observed that fairness is not just a technical issue, and in order to ensure algorithmic fairness, multiple perspectives, particularly that of domain experts, the product specialists, have to be taken into consideration so that we are adequately addressing both the performance and risk trade-off for these models. So based on these learnings, what we envision is that we have to move towards the adoption of a new data science lifecycle, which is not focused only on performance optimization, but at every step of the data science lifecycle, fairness considerations are addressed. So starting from the data processing stage with assessment of the historic bias contained in the data during the model development process to not only include the accuracy and performance metrics, but also simultaneously optimize for the fairness metrics, all the way post-deployment of the models to monitor performance as well as fairness, because data drift could eventually turn a fair model into an unfair model. So in summary, we see the data that we use to train models often contain historic biases, and the algorithms can not only inherit, but amplify and perpetuate these existing social biases. Hence, for us, it is imperative to ensure algorithmic fairness, particularly for us in financial sectors, in heavily regulated sectors. And we see how with the UBS FAIR initiative, we are trying to address some of these challenges. We are in fact very much in the early stages of this process, and in the future we plan to incorporate more devising algorithms and metrics and apply this to diverse use cases, based on which we can collect the learnings, and in future these will contribute towards the incorporation of these learnings into a standardized model governance framework at UBS. Thank you. That is the end of the presentation, and we are happy to take questions.
Thank you very much, all of you, for the nice presentation and bringing bias and fairness here. Questions? There in the very end.
Thank you very much for the great presentation. It was very insightful and I think highly relevant for all the participants of this conference. I was a bit surprised by the result you presented in your small example with respect to age, that the performance of the model actually increased by introducing fairness constraints. I would have expected that there is kind of a trade-off between performance of a model and, on the other side, fairness of a model. Can you briefly comment, maybe also from a practical point of view, how you're dealing with this exact trade-off, and whether the results you showed is kind of representative, or whether you also see exactly the opposite, where model performance significantly decreases and you in the end have to decide between fairness and performance?
Yes, that's a great question. And in fact, with this example, what we saw is there was an overall increase for F1 score by the model. So the business requirements indeed actually translated to have a high precision model. And with respect to precision, after addressing the fairness constraint, indeed there was a drop in precision. So there are simultaneously all these different metrics that we are monitoring. And indeed this is similar to observations in the literature that there is a trade-off. It was with respect to the drop was for precision, but due to the increase in the very high increase in the recall, the F1 score increased in this case. So it is indeed consistent with the observation that fairness constraint leads to some trade-off for the performance also.
Thank you very much.
Thanks. Luca from Swiss Re. To follow up on the previous question, debiasing the algorithm really changes the operating point of your model. Decreases precision, increases recall. What if this point is no longer sustainable from a business point of view? Whether you cannot make money out of it?
Yes, indeed. That's a great question, and this is sort of what we have looked at with just numbers at this point, but we saw there are new publications which enable us to actually go into detail to really investigate this further, and we haven't really incorporated the cost at this point in this consideration and just looked at the metrics from the model. So using the utility of the different types of error, we can indeed look at what you mentioned, but this, so far, we haven't really addressed it.
May I just
Sure.
add something very quickly? I mean, unfortunately, there is no single answer to this question. You heard already that fairness is not a technical problem, and that's our position as well. It's very use case specific. So in those situations, to be blunt, I don't know. We'll have to have the discussions, and then we'll know.
I think perhaps to add here that there are these new laws coming from European Union and also Swiss Parliament around what fine do companies will have to pay if they do not follow the fairness and ethical practices in decision making. So the price tag you're asking for actually is associated with that primarily. If I make an unethical decision, what do my company have to pay? Is it a price with respect to my image of the company or something else?
Well, the regulators also kind of ask us what's sensible.
Yes.
So it's a conversation.
But, I mean, a quick follow-up also, to compensate for the decrease in the performance of a model, you might need to increase the price. And is that fair to increase the price for the entire population?
Good point.
Is it?
I think, yeah, like Pavel mentioned, I mean, this is going to be an iterative process, right? So we see some discrepancies, and we go back to the stakeholders, and we discuss the costs and versus benefits. And also, I think to this front, I think adding model explainability would help, because that will help us understand where the root causes are. And then we can go back and either we fix the data or fix the model. And yeah, of course, yeah, it's going to be like human in the loop process. Yeah.
Yes, in the front here.
I've understood in how far the distribution of the data could be biased, but I've not understood in how you could detect bias in the ground truth as such. You know, whether someone really wants to be contacted digitally, or is it just to have a nice dinner or lunch with client advisor, then I probably would prefer that, but so forth. So how do you know whether the ground truth is actually ground truth? Does the the whole procedure actually
somehow
help?
artifact of the
Continue with the Q&A.
data collection process. Yeah, that's a great question. So for these, when we say that the bias from the data, we are, with this matrix, the disparate impact ratio. So it's a ratio of the proportion of positive outcomes in the two subgroups under consideration. And so when we see for age, there is a deviation, and it indicates that it's younger populations who have higher rates of adoption of digital, say, modes of communication. This, for example, is sort of expected. It's not really contrary to our expectation. So in this case, we see this as a reflection of client preference, but of course, we have not really validated whether, you know, the value that we observe here is really the ideal value. We have not. This could require, say, further investigation.
One last question, perhaps. Maybe I have one, the last one. So there is one part around when you talk about ethical. Oh, there is one in the audience? Yeah. Sorry.
There is a follow-up question from my side. At the very root of your problem setting, there is actually the question about fairness as such, and depending on how you slice and dice the data, actually you could finally, in an extreme case, create a model for each and every individual, right? So is there kind of a common agreement about the dimensions of data which should always be included in your considerations? Is this kind of a company guideline? Are there general guidelines which you can follow? Can you maybe briefly comment on that as well?
Yeah. Okay. Yeah, I can get started. I mean, I think that's a great question, and it's also a central topic that we are having right now, both internally and also I think in the regulatory bodies. I mean, for now, I don't think we have a definitive list of sensitive attributes. I think there are already laws regarding the specific domains. For example, in the US, for HR-specific analytics, there are laws that require on these dimensions there shouldn't be too much discrepancy. But from a technical perspective, I think it's also good to take a data-driven approach, right? So, I mean, it's very easy to loop through all different combinations and see if there are discrepancies. And if there are, then we try to understand. But yeah, I agree that long term, it's best that we can get that definition from either laws or regulations.
May I just add something again very quickly? I mean, look, ultimately, you know, every machine learning model, the purpose of it is to discriminate, right? So as best as possible. So you always have this tension, and the question is actually in which cases is discrimination justifiable? And that's why technical tools can only focus on giving humans the diagnostic tools, measurements, metrics, whatever, to answer these questions. Is this discrimination justifiable? So it doesn't matter if you have one specific model for every customer or one huge monster model, you will always reach this point where is discrimination justifiable becomes relevant. So the best we hope to do with a technical tool is offer insights, diagnostic insights. So that's where kind of Python stops being useful.
Thank you very much, all three of you, for bringing this point around responsible AI. And yeah, thank you very much again for the nice presentation.
Thank you, everybody.
We have something for you
Thanks a lot.
for the summer, the heat outside. There you go. Thank you very much.
Thank you.
Thank you so much.